Welcome to the Aaron Harber Show. My guest today is Lynn of Princeton University. Thanks for joining me.
Thanks for having me, Aaron.
It's great having you, Lynn. Of course, you're a professor at Princeton. You're director of the Anlinger Center, and I want to talk about the center. I'm very interested in nanotechnology and some of your work in that arena in particular. So first, tell me a little bit about the center.
Okay. So the center is called Anlinger Center for Energy and the Environment. It was established in 2008 through the generosity of Gary Anlinger. And I came on board as the associate director in 2012. The mission of the center is to develop solutions for our energy and environmental future. It sits in the School of Engineering and Applied Science, but it's got tentacles because, solving the world's energy problem is going to require multiple disciplines. So we've got joint appointments in the Woodrow Wilson School, in psychology, in architecture, and then, of course, in engineering and in the sciences. So we have about 10 joint faculty. The way I like to see this is that it's like a hybrid department. These are all joint faculty, so they have joint appointments with home departments. And then we have about 120 faculty members from across campus that are associated with the Anlinger Center. So that's sort of the size of the Anlinger Center in terms of what we do to move towards our mission. Just to put things into context, right? I mean, the energy challenge is a huge challenge today, right? We take for granted when we flip a switch that we have access to light. It's always there. It's reliable. But there's a billion people without light today. And with population growth, and then with this billion people moving into the middle class, there's going to be a tremendous need for more energy. But at the same time, we're looking at greenhouse gas emissions. So we need to reduce greenhouse gas emissions associated with energy at the same time in providing these folks with energy. So that's the dual energy challenge. And so to our work at the Anlinger Center to look at this mission is I would say threefold. I mean, fundamentally, we're an academic institution. So we do research, and we develop technological solutions and solutions more broadly. And so I can give you a couple of examples of the things we do. For example, one of my faculty colleagues, she develops green cements. So this is cements that produce less carbon dioxide. For every ton of cement you produce a ton of carbon dioxide. That's the Portland cement. So if you can get a different chemistry that produces cement with reduced carbon dioxide, that goes a long ways towards reducing carbon emissions.
So two things. One, what kind of reduction are we looking at? Assuming the standard cement is 100%, what kind of reduction is she trying to
So
achieve?
it depends on the chemistry, and so when you produce cement, there are two ways that you're producing carbon dioxide. One's in the chemistry, inherent in the chemistry, and then the other is in the process. The process is very, very energy intensive, and so depending on the chemistry, you could reduce it perhaps half, perhaps 80%. I think it depends on the chemistry that you're using. Some of the chemistries actually calls for you impregnating carbon dioxide into the cement itself. Now, those are all very early on, so those are all in development.
Great use of carbon dioxide.
Yes, yes, yes. And I mean, you need to think about ways to use it. So that's the utility part of carbon dioxide.
So she's shooting for at least a 50% overall reduction?
Well, I think that's the target, but there are lots of hurdles before getting to that. And as an academic institution, what we are fortunate and privileged in being able to do is to focus on the fundamentals. So getting the chemistry right, understanding the chemistry, and what she's also doing is conducting accelerated testing, right? Because if I were to come to you and say, hey, use my cement instead of Portland cement, you're going to ask, well, how robust is it? Am I going to build a bridge with your cement as opposed to something that's been tested, for decades? So she's doing accelerated testing to show the mechanical integrity of the material. So that's just one example.
All right, and before we leave cement, I think a lot of people don't have any conception how significant cement's contribution to greenhouse gases is. Talk just a little bit about that.
So it's about 5 to 8% of total greenhouse gas emissions, and
that's an extraordinary number.
Yeah, well, for a single material or a single use, it is huge. It's the second largest used in terms of material. The first would be water, and then cement would be the second, because it's used in all materials. It's an infrastructural material.
Where does it rate with cow flatulence?
Oh.
Tough question?
Yeah,
No?
Yeah, I don't know the answer to that. I know cement is intense.
We'll have it on the screen. All right, keep going. That was one example.
That was one example. In our lab, we developed solar cells that absorb sunlight to convert sunlight into electricity. You see a lot of them on roofs today. Ours is an emerging technology. We developed solar cells that absorb ultraviolet light. So these things are essentially transparent. But it's an oxymoron, right? If it's transparent, it absorbs less light, so it generates less electricity, but you're calling it a solar cell. We think there's a different application. That's to use it in windows. And then we use these solar cells to then power an electrically dimmable film. So the ultimate product is a self-powered, electrically dimmable window retrofit. So in 2050, 50% of the buildings that are going to be used in 2050 have already been built. Okay, these buildings could have various levels of energy efficiency.
2050.
2050, yeah. And 50% of the buildings that will be standing in 2050 have already been built. So retrofits is a hugely important market, demand, whatever you want to call it. So we're hoping to address that by this self-powered, electrically dimmable window retrofit. So the idea is you pop this into your window, and you can basically have a switch or wirelessly control it from your phone. And if you'd like to darken it, you click a switch or you tell your phone to darken it. And when it's dark, it regulates or it limits the transmission of light and heat into your building, so you can use less air conditioning, you don't have to turn on the lights. So it's to reduce heating, lighting, and cooling costs within building to increase energy efficiency.
Now, will you be able to generate electricity from it for other uses?
So because we're only absorbing the ultraviolet portion, because we want to keep it transparent, and the other thing is we wanted to decouple it from the visible portion and the infrared portion, because we think that the other portions of the solar spectrum are better used when you are able to manage it in the form of light and heat. So we only absorb the ultraviolet portion. And so we generate a little more energy than we need for the window, and we use that energy to then power, for example, controls. And we have a little battery so that you can use this window while it's cloudy out or when it's rainy out. And that little control allows it to talk to your phone so that you can turn it on and off.
All right, so are these smart windows?
These would be smart windows, yes.
Okay,
yes.
Great. Example number 3, please.
Let's see. So example number 3. I have a colleague who is a cognitive psychologist by training, and she's interested in how human beings make decisions. And of course, in the world of sustainability, or when you're talking about energy technologies, this is greatly important when you're thinking about deploying specific technologies. So she studies that, and she studies that, and so that she can help different, to understand how human beings make decisions, so that we can help entice, incentivize, whatever you want to say, encourage people along the right path. So that would be example number 3.
Anything that she's come out with of interest, or?
Yeah, tons. So how you, so if you give, let's just say, if you give your audience choices, the sequence with which you lay the choices matter, and preference goes to the first. So that I thought was interesting.
Yeah, I would have thought the opposite.
No, yeah, and then she talks about.
For example, if you're in a group of people that are speaking,
right,
you always want to be the last to speak.
Why?
Because that's the most significant impression that will be left with someone.
Huh.
So that's her research. That's why I'm really.
Yeah.
I'd like to see that. I disagree with her finding.
Okay.
Tell her that.
and I mean, and she says it. Humans are. We'd like to think of human beings as rational beings, but we're very far from rational.
I won't argue with you about that.
And she talks about the fear factor, right? How there's sort of fear, and if you push somebody apart, everybody's threshold is different, and if you push somebody above that threshold, it goes into, you cripple the person, and so they wouldn't be able to make decisions. So you want to push them up to the point so that you raise their awareness, but not above the threshold, so to cripple them.
That's fascinating. I'd like to see how that applies and what the threshold is for people who don't believe in climate change, for example.
Yeah, well, we won't go there. We won't go there. But I mean, nuclear, for example, right? And so those are examples that should give and should show sort of how people's sensitivity is along different axes in terms of fear. So that, I think, is interesting and very enlightening and illuminating in terms of what we do and in casting it in the context of what we do. I do want to mention one project that I am super excited about. So this is a project we just recently launched, and we launched it at the center level. So this is called Rapid Switch. So switch refers to a switch from a fossil fuel-based infrastructure to a low-carbon infrastructure. Here we're basically taking a pragmatic approach and asking ourselves, how fast can we decarbonize? What are the bottlenecks and the constraints that are in place that are limiting the pace with which we're decarbonizing? And if we can identify them, and they're necessarily different from region to region and sector to sector, then we can figure out ways to overcome them. So this is a project that involves social scientists because the bottlenecks could be socioeconomic in nature. They involve political scientists because it could be policy in nature, technology in nature, so engineers and scientists. And so I'm super excited about this project and how it's bringing everybody together.
So is that project looking at, for example, sources of greenhouse gases and solutions to address the needs those sources meet that are not as carbon intense, and saying here's the path, this path's difficult and why, but over here's another source where the path is a lot easier, so let's do that first, or what?
Yeah, well, I mean, sort of. So because if you look at where emissions are coming from, I think the big piece is China. That's 25% of our annual emissions. And then if you look at India, India is projected to be, the most populated of these emitting nations, with an economy the size of China's by mid-century. So the tiny slice of emissions that's 1 to 2 gigatons a year right now is going to grow, right? So we have projects and initiatives in these areas because we think understanding what the bottlenecks in these areas are will help us move the needle. So if you look at these two areas, the bottlenecks are quite different, and you have to look at very specific sectors. So, for example, in China, 40 gigawatts of coal-burning power plants have just been brought online. These coal-burning power plants all have an economic life of, 50, 60 years?
And they're still building new plants.
Yeah, they are still building new plants. And so if you look at these models that call for early retirement of coal fleets, that means all these coal plants are going to be stranded assets. And if you estimate what the stranded asset is to the tune of $400 billion.
It's a lot of money.
Well, that's a huge bottleneck, right? And so how do you address this bottleneck? So that's sort of something that we're looking at. Another example would be, again, in China. So where would you put wind turbines and wind projects in China? It would be sort of inner China, Mongolia, those kinds of areas. But where do you need electricity the most? It would be coastal cities.
Huge transmission issue.
Yep. Yep. How do you do that, right? So that's a more of a technological challenge, if you will. Another example, CCS, so carbon capture and sequestration. If you believe the numbers in the projections, it calls for a lot of carbon capture and sequestration across the nations. But the U.S. is the only nation, I would say, one of the few nations that is fortunate enough to have the right geological formation to be able to store carbon dioxide. So if you go to China and India, there's less of that. So you'd have to think about oceans and things of that sort. So let's just think about capacity. The amount of carbon dioxide that's called for sequestration is 2 to 3 times the historical volume of oil and gas extracted from those regions. So where are you going to put carbon dioxide? That's another question that one would ask.
All right,
fun questions. So those are the kinds of questions. Yeah.
You're lucky to be doing this. You know that.
Yeah. I can't
argue with that.
No.
All right, we're going to take a break. We'll be back with Professor Lynn Liu in just a moment.
For information on how to help promote civil and mutually respectful discourse and support expansion of the distribution of our programs, please email info@harbertv.com.
I'm Aaron Harber, host of The Aaron Harber Show. I very much would like to hear from you about the program, so please send me an email with your thoughts. You can suggest what topics I should cover, what guests I should invite to be on the show, or even what specific questions you would like me to ask. This is your program, so send your suggestions to aaron@harbertv.com. I promise to personally read every one, so email me today. And most of all, thanks for watching.
Join me and watch The Aaron Harber Show.
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 I'm Reverend Jesse Jackson. Watch The Aaron Harber Show and Keep Hope Alive.
I'm Aaron Harber, host of The Aaron Harber Show. You can follow the show on Twitter for instant notification of new episodes, live event invitations, outtakes, and behind-the-scene photos. And tweet us your topic and guest suggestions today.
The Aaron Harber Show may be viewed 24/7 at no charge from any location in the world at harbertv.com.
Welcome back to the show. We're with Professor Lynn Liu. So you call yourself a non-traditional chemical engineer. What does that mean?
In lots of different ways, I suppose. My degree is in chemical engineering. I don't so much practice chemical engineering. I consider myself a material scientist, a polymer scientist. That's what I trained as a polymer scientist. And now I'm using the fundamentals that I learned as a polymer scientist, as a chemical engineer, as a material scientist, if you will, to make solar cells. So we're increasingly moving towards energy applications because this is what I'm passionate about.
What about in terms of, as you look at the number of women going into these fields? I mean, 20 years ago, really tiny numbers. How's it changed? What kind of role model are you? Whether you like it or not, you're a role model. Being a minority and all that. How is that? How has your path been with all those factors?
So I think chemical engineering has been. So it depends on at what level you're talking about. At the undergraduate level at Princeton, in the chemical engineering department, we're more than 50% women.
Which is extraordinary.
Absolutely. And I think in part that's, I think if you look at studies, studies would say that women are attracted to wanting to make an impact. And so anything associated with, if you can see the application at the end of the day, I think that's more attractive. And so with chemical, and so our department's chemical and biological engineering. And so that, I think that biology component has brought a lot of women into the field. At the graduate level, we have a third women, and then at the faculty level, I'm one of 2 out of a faculty of 18. So you can see there's a pipeline problem there that we're actively working on it.
Got to open a few tenured positions up.
Well, we have tenured positions, and so it's a matter of getting good women to apply, and then I think bulking up the pipeline before they enter.
It takes a long time.
It does.
But you're good at shortcuts, so just develop an app for that. That's it. Rapid tenure or something like that.
I don't know whether that can happen.
Talk about thin film electronics.
Okay. So thin film electronics, the idea of thin film electronics is you're making electronics lightweight, flexible, could potentially be low cost. Low cost from a manufacturing standpoint because you can paint it on or you can inkjet it on. And so we work with organic molecules, so molecules that contain carbon, hydrogen, oxygen, and we use these molecules to make electronics. So it's very different from if you were to use silicon to make electronics. I mean, I think with silicon, it's very brittle, you can break it. So with organics, if you spread it over large areas, you don't worry about, the mechanical properties are very different. So you can begin to think about conformal electronics, right? Things that conform or things that can be woven into your textiles and electronics that function, that have multiple functions.
Yes, I hear that Vladimir Putin wears all kinds of clothing with that technology.
Is that right?
Yeah, electronic clothing. No, I'm just kidding. I'm just kidding. So what's that mean for the future in terms of some of the applications?
Yeah, I think for us, we're excited about these molecules because they have attributes that are very different from the inorganic counterparts. I've already mentioned silicon. Silicon will give you better performance, so you can make a computer with silicon chips and it runs at gigahertz or tens of gigahertz. If you were to make the analogous computer with our material, it would only run at kilohertz, right? So you wouldn't want to target silicon necessarily as your competitor. But what we have are mechanical flexibility. It's lightweight, and its properties are tunable depending on the chemistry with which you make it. And so, for example, coming back to the ultraviolet solar cell, we're able to tune its absorption all the way into ultraviolet, and so we're only absorbing ultraviolet light. So that's the chemical versatility that comes with these materials.
And pretty thin, too.
Yes, yes, absolutely. Yeah, I mean, so the active layers in these things, so in our particular ultraviolet solar cells, they're only about 40 nanometers. So they're one-tenth of the width of a human hair.
Yeah, that's small. Okay, we talked a little, not much about organic cells. I know we're about to end this segment, but give me a quick take on what you're doing in that arena.
So the organic cells are the ultraviolet cells that I talked about. The other things that we work with are hybrid cells. So these are hybrid inorganic and organic. So we're trying to get the best of both worlds. So this is a class of material called perovskites. So they have an inorganic component and an organic component. The inorganic component gives you the electrical performance. The organic component gives you the processability.
So you're taking the best of both worlds.
Yeah.
Very smart. I'm not surprised. All right, we're going to take our last break. We will be back with Professor Liu in just a moment.
For information on how to help promote civil and mutually respectful discourse and support expansion of the distribution of our programs, please email info@harbertv.com.
I'm Aaron Harber, host of The Aaron Harber Show. Find us on Facebook to get all the latest updates, see behind-the-scenes photos, and make comments and ask me questions. You can see episodes before their TV broadcast, so like the show today. I'm Aaron Harber, host of The Aaron Harber Show. You can follow the show on Twitter for instant notification of new episodes, live event invitations, outtakes, and behind-the-scenes photos. And tweet us your topic and guest suggestions today.
Join me and watch the Aaron Harber Show.
Watch the Aaron Harber Show.
Watch the Aaron Harber Show.
Watch the Aaron Harper Show.
Watch the Aaron Harber Show.
I'm Reverend Jesse Jackson. Watch the Aaron Harber Show and Keep Hope Alive.
The Aaron Harber Show may be viewed 24/7 at no charge from any location in the world at harbertv.com.
Welcome back to the show. I am with Professor Lynn Liu of Princeton University. So, Lynn, tell me about the E-affiliates, the Princeton E-affiliates program, and what was the catalyst for that?
So this was something I started when I was Associate Director at the Andlinger Center. Given our mission, I thought it was very important for us to partner with industry. And so I started a corporate affiliates program, and we call that Princeton E-affiliates Partnership. And really, there are three goals associated with this program. One is to lower the barrier for collaboration between industrial researchers and our faculty members. Industrial researchers bring a very unique perspective that we don't have, and so that's important. Two is to help facilitate technology transfer when technology is ready. And three, from an education perspective, is to provide our students well-rounded student-teacher-practitioner interactions, because we don't do the practitioner piece very well. So that's the corporate affiliates program, and we have probably 7 or 8 members who are with us.
Who's in it? Tell me who's in it.
So we've got ExxonMobil. We've got PSEG, which is New Jersey's largest utility company. We've got NRG, another utility company.
It's NRG, and it took me a year before I realized that if you say it quickly, it's energy.
Oh, yeah, that's the whole point.
I know. I know. David Crane used to run that, and he lives
he's
in Princeton.
Yeah, that's right. He's a good friend of the center.
Yeah, he's retired though.
Yes, yes. I think he's consulting them now. So that's a corporate affiliates program, and it's been really good because it's really allowed for these kinds of interactions that would not have happened otherwise. And I would say that, for us, it's as a center, we're an academic institution, so part of our responsibility is to contextualize the complexity and the scale of the energy system to our stakeholders. And our stakeholders could be corporate partners. Of course, they're students. And we're using these opportunities to tap into decision makers as well. And so we actually started, I'm super proud of this, Princeton's first executive education module on energy technologies. And so so this is in partnership with the World Economic Forum. So this Young Global Leaders cohort come, and so we teach them what's a joule, what's the difference between a joule and a watt. And
You're talking energy.
Yeah, and we start with basic thermodynamics.
You say joule to most people, and they're spelling it differently, by the way.
How differently would they? Oh, okay, joule, I get it. I'm telling you, English is my second language. But yeah, so that's been tremendously successful, so we're going to do it again. So
with the partnership program, do students get a chance to go to any of these companies?
Yeah, absolutely. So, so it's a two-way street. So absolutely, we schedule tours, and we bring actually practitioners in to talk to them about careers. And we have annual meetings and retreats that are specifically for our corporate partners, and we encourage our students to present posters at these annual meetings to, again, increase the chance of collision between them and our industrial partners. Okay,
well, and I don't mean to offend you, but it seems every institution of higher education has some kind of energy and environment center. First of all, two quick questions. One, I know we're running out of time. Do you have any idea how many of these there are?
A ton.
Well, that's not exactly a numeric, like a few hundred, it seems.
A lot, yes.
And is there any coordination of academic work, goals, is there any collaboration between any of these?
So I think there are on a research level. So through big major funding initiatives through the DOE, there are collaborations, and it could be clusters of faculty at one working with a cluster of faculty at another. I think so. I'm thinking of some right now, and I'm drawing a blank. But so these kinds of collaborations happen all the time, and these kinds of collaborations happen sort of at the grassroots level. So it's at the faculty level. It'd be nice to have some kind of a coordination, and we're thinking about putting something like this together.
All right, because I do a lot of programming in the energy space, and so I've just been astounded by, and we work with. Mighty at MIT, for example, and we work with some other schools.
Well, I hope you work with us.
Well, I will see if my boss, my producer, will allow me to do so, but that's something we certainly could do. Professor, thank you so much.
Thank you for having me.
My pleasure. All right, that was Professor Lynn Liu of Princeton University. I'm Aaron Harber. Thanks for watching.
Please contact us. We want to hear from you. And thanks for watching.
The Rexall Broadcaster of the Year Award recognizes an individual who, through leadership, skill, and dedication, is advancing the broadcast industry in our state and our nation. Tonight, we honor Aaron Harber. Aaron has worked extensively in the media as a host, producer, political and economic commentator, and columnist. Today, the Aaron Harber Show is the focus of his media involvement. Aaron, it is a privilege to present you with the Rexall Broadcaster of the Year Award. Congratulations.